In one sentence, can you summarize inflation, please?
The accelerated expansion of the universe at the beginning.
Hello, and welcome back to Physics Chat. My name is Susanna, and I'm here with my amazing co-hosts, Joe and Sergi. Physics Chat is a show where we talk to real-life researchers at the front of their research, as well as hearing their unique journey into research. On today's show, we have the absolutely lovely Joe Jackson. Hello, Joe. How are you doing?
Thanks. I'm pretty good. I'm actually coming to you live from Paris today because I'm visiting here as part of my research. So that's pretty cool. That's
very exciting. How is Paris?
Yeah, nice. Plenty of nice croissants and stuff. And it's nice and cool here at the moment, although I'm a bit worried when it starts heating up in a few months' time because I don't deal well with the heat.
That sounds so good. Joe is a second-year PhD student researching inflation of the universe. And we have two Joes on the show. So this is going to keep me and our audience awake. But first, tell us, Joe, what is our current understanding of how the universe started?
So our current understanding is that the universe started in some very, very hot, dense state and then rapidly expanded out of that hot, dense state. Notice I didn't use the word Big Bang because Big Bang, to me, implies it started as a point. Whereas the idea is that the universe expanded everywhere all at once. So I don't really like the idea. I don't like to use the term Big Bang because it's some hot, dense part. The universe started in a hot, dense state and then expanded rapidly everywhere is our best understanding.
Yeah, I haven't heard someone go against calling it Big Bang. That's quite interesting. But with this hot, dense state, at least I know when I was first introduced to me, it was kind of like, here's what it is. It's all good. But are there any problems with it? Anything we don't understand about it fully?
Yes, there's a few issues we're just assuming we need to solve to explain it. First one, why is the hot, dense state expanding very, very rapidly? That's quite a simple solution of current theories of gravity tell us why. But that's sort of a trivial one. The main issue, though, is that why is it so uniform at the start? Because you start off with something that's then expanded outwards. It means, everything's expanding. It means that one side of the universe hasn't actually been in contact with the other side of the universe unless it started right next to each other. So the idea of inflation is that everything started very, very, universe was in a very, very, very hot and dense state. So everything was next to each other, was in causal contact, could share light, and then rapidly expanded away from everything else. So that's the first issue. The second issue is that we observe galaxies. But if you have some hot, dense state that's very uniform, because all in contact with each other, there's no seeds for those galaxies, because it could be you just have some cloud of dust and radiation, and that just expands uniformly, and the density just goes down, and no structure forms. You need small fluctuations, which we call perturbations, in that gas to then collapse gravitationally to form galaxies. That's where the idea of inflation comes in, because inflation naturally leads to small perturbations.
So there are a few terms that you introduced here, Joe. First of all, perturbations. Can you explain what you mean by perturbations?
The idea of perturbations, let's say you have a swimming pool, and it has all the water's nice and flat in the swimming pool, and you just dip your finger in it, and it causes little waves on the swimming pool. If you compare the size of those waves to the depth of the swimming pool, they're very, very small. There's tiny little fluctuations. That's the idea of a perturbation.
These small perturbations that then, with the help of inflation, give rise to the structure that we see, the galaxies and stuff. Okay.
You need them because they eventually grow gravity. So as the universe expands, locally gravitate, because they're local events, that locally gravity causes them to get denser and denser and denser. And eventually they can then form galaxies. Okay. So if everything's absolutely perfectly uniform, galaxies can't form. You need the little seeds for them to gravitationally.
Joe, what do you mean then by space expanding? Like, I can kind of get the idea of something expanding into space, but what happens when it expands itself?
The idea is not that the universe is expanding into anything. All of space as time is expanding. So maybe an illustration will make this a bit easier. So let's say you have a shoreline here, and you have a river going into the sea. The water will then expand out into the sea. And if you have two little rubber ducks, I can't draw rubber ducks very well. Imagine there's some little rubber ducks here. They would move away from each other with the sea expanding. So they would expand, they'd move away from each other with the ocean. although in this case, the river is expanding into something, the universe is not expanding into anything, everything just expanding away from everything else. Hopefully, this gives across the idea of space itself expanding.
I like the idea of having more like the stuff in the universe is getting further away from each other, I guess is the way that we understand it rather, because as you said, space expanding itself is really hard to understand, but you can see what that would result in is quite a useful way. Yeah, thank you. But what observational evidence do we have then for inflation?
Don't directly observe inflation. It just explains. It's a very good explanation for all of what we observe. So we observe the universe as flat, but we observe one side of the universe look the same as the other, and we observe galaxies. And inflation explains all of that. But it's sort of the sort of key, almost smoking gun explanation is that very distant light, which we get the first light we can observe, which comes from something called the cosmic microwave background, so background radiation. That light, the distribution of the perturbations we observe from that light is exactly what inflation is. So it has a predictive power, and it made a prediction. We then sent a satellite and observed exactly what inflation predicted. So it's not been directly confirmed, but it explains everything very, very well.
So what is your research adding to our understanding of inflation?
My research is looking at some extra predictions of inflation. It could be that very large perturbations in the universe could then collapse to form black holes before stars form. And my research is about seeing if that is physically possible. And then if it's physically possible, seeing predicting what the distribution of those black holes before stars forming is. Because if we then observe those, that's even more evidence for inflation. Because if you can't have, otherwise, how can you explain black holes forming before stars without inflation? So that's sort of it. My research is about coming up with extra predictions from inflation to then confirm it more with observation.
Okay, wow. So these are black holes formed during inflation.
Just after inflation,
and they're called primordial black holes, right? That's
the
only inflation is the only way we can get those primordial black holes.
Not the only way.
Okay.
But it's one of the major ones.
It would be a strong evidence for inflation.
Strong evidence. The truth is with physics, there's always some crazy theory who comes up with something completely crazy. There's another way to do it. But that would be the most likely way. Modern physics, you very rarely completely 100% confirm something. You just confirm it to you're just 99.9999999% sure that is the explanation.
Could you say something more about these primordial black holes? What is their mass? Have we observed them, or can we observe them in any way? Can we differentiate them from normal black holes now?
It's very hard to differentiate them from normal black holes because inherently a black hole is just an overdense object. The only way you can differentiate them is by their mass. If they are not in the mass ranges that we observe from stars forming, for example, if they're less than the mass of stars, much, much less than the mass of stars, they could not have formed from stars collapsing. Or if they're much, 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 much larger than what we expect stars to be able to collapse to, that would also be evidence for it. We can't directly look at one and say that's a primordial black hole and that's a stellar mass black hole because they're just a very, very dense object. So it has to be in a mass range we don't expect.
Joe, thank you so much for chatting us about your research and primordial black holes. Who knew they were so cool? But I also know you like baking. And the reason is I've had the huge privilege of trying your amazing cakes. So this is the part of the show where I just ask a completely random question. So tell me, what is your favourite cake?
It's a hard one because I like lots of different cakes. It's between brownies and fruit cake. It depends on what I'm having. If I'm having a cup of tea, I want brownies. The fruit cake, we're having coffee. I want a brownie.
Nice. What about you, Sergi?
It's a difficult choice, but I won't overthink it. I'll say cheesecake.
Ooh, very nice. And what about you, Joe?
If we're limiting it to cakes, then it would have to be carrot cake, just for the novelty when I was first told it and how it sounds disgusting. But then you eat it, it's all right.
Nice. Yeah, I actually agree with you. I think carrot cake is my favourite cake. I love a carrot cake, especially when they've got sultanas and walnuts in. That's amazing.
Correct.
Anyway, the other day I found something so interesting about you, Joe. You were homeschooled. So could you explain what homeschooling is?
Yes, so homeschooling in the UK is the idea of just having education outside of a schooling environment. There's a broad range of this. So this can be literally following the same school curriculum, just at home, or it can be doing something completely different and spending all of your time just focusing on music. There's a very broad, each family does homeschooling differently. So I spent a lot of my time doing history and science, but that was out of my own time rather than following an official curriculum.
Yeah, Joe, it's really interesting to hear about the differences that you would find between a normal school and homeschooling. How do you think it prepared you for becoming a PhD student and doing academic research?
It particularly helps because you're encouraged to be curious and self-motivated, because you haven't got a teacher looking over your shoulder telling you you've got to do this work. You have to do it yourself. You have to, if you're curious about something, you have to go online, or back when I was a kid, you have to ask your mum to go to the library and take out a book of what you're interested in. You need to read it yourself. And it sort of encourages you from a very young age to be motivated and curious. And those are two very key sort of characteristics of research. And you have to be curious about finding out why the universe is how it is, and you have to be motivated to put in the time, because sometimes research doesn't always go the way you want it to, and you hit a dead brick wall for a long time. You need to be motivated to know that you can figure out a way around these problems, or go into a different field, or whatever it is. You need that motivation. So it has definitely helped me in that regard.
So is there any advice you'd give to anyone out there who is homeschooled and is considering pursuing physics?
For the reasons I just said, you're already going to be self-motivated and you're already going to be curious. Those sort of two key characteristics. The more boring thing is you need to be good at maths. So that's just for going into physics research.
Well, I hope this encourages you all to go and get a pen and some paper and do some maths now. But I hope all my favourite homeschoolers out there are encouraged not to let their type of education be a barrier, but rather as an opportunity to follow their dreams, like Joe did. So Joe, thank you so much for being on Physics Chat, and we wish you all the best in your PhD. Let us know in the comments section what your favourite cake is. We would love to hear from you, so keep writing. That is just now my thing, so you're just going to have to deal with it. Anyway, from everyone at Field of View, we hope you have a great day, and goodbye. Bye.
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 Bye. There's always some crazy theory.
She says bye, and after we say bye,
Yeah,
right?
okay, that's fine.
Together. Do you remember that song? Head, shoulders, knees and toes.
I remember this song.